Ever wondered how networks prevent looping within their network topology? It's an intriguing question, right? Well, let's dive into it. In the realm of networking, a loop refers to the situation where more than one path leads from a particular source to a specific destination. This might sound like a beneficial redundancy at first, but it can lead to some severe issues. For instance, imagine a packet of data like a tiny digital postman trying to deliver information from point A to point B, but instead of a straightforward route, our little postman encounters multiple paths. He gets confused, starts running in circles, and the information never reaches its destination. This is a classic example of a network loop causing inefficiency and congestion. But there's more. Network loops can cause broadcast storms. This is when broadcast messages sent to all devices on a network start to multiply and loop around the network. It's like a digital echo, getting louder and more chaotic until it consumes all available network bandwidth. This can bring a network to its knees, causing slow performance or even total failure. Now, wouldn't it be fantastic if there was a way to prevent these loops from happening in the first place? Well, there is. And it's called the Spanning Tree Protocol, or STP for short. STP is a knight in shining armor for network engineers, a layer 2 network protocol specifically designed to prevent looping within a network topology. It's like a digital traffic cop, directing our data postman along the correct path and preventing him from getting caught in a loop. STP effectively eliminates redundant paths, leaving just one active path between any two network nodes. But it's smart too. If the active path becomes unavailable for any reason, STP can activate a previously blocked path. This way, it ensures continuous loop-free communication within the network. Now that we know what network loops are and why they're problematic, we can delve into the solutions, starting with the Spanning Tree Protocol. So, stick around because things are about to get even more exciting. Spanning Tree Protocol, or STP, is a crucial part of preventing network loops. But how does it work? Well, in essence, STP is a network protocol that operates at the data link layer of the Open System Interconnection (OSI) model to prevent loops by creating a loop-free topology for Ethernet networks. Let's dive a bit deeper. In a network, multiple paths between switches can cause loops, a situation that can lead to a variety of problems such as broadcast storms or multiple frame transmission. This is where STP comes into play. It identifies redundant paths and disables them, leaving a single active path between network nodes. Now, how does STP identify which paths to disable? This is where the concept of the root bridge comes into play. The root bridge is the main switch in a network, and all the paths in the network start from this point. STP elects the root bridge based on the Bridge Protocol Data Units (BPDU) that the switches in the network send out. Once the root bridge is chosen, the next step is to determine the best path from the root bridge to all other network nodes. The criteria for the best path is typically the path with the lowest cost, which is calculated based on the speed of the link. The ports that provide the best path to the root bridge are designated as designated ports. But what about the other ports? They are put into a blocking state to prevent loops. These blocking ports won't forward frames. They simply listen to the network to determine when they should transition to forwarding state. This mechanism ensures a loop-free topology in the network. Now remember that STP is dynamic. It constantly checks the network for changes and recalculates paths if a change is detected. For instance, if a designated port or a link fails, STP will reconfigure the network to ensure continuous operation. However, while STP is a powerful tool for preventing network loops, it's not perfect. For instance, the time it takes for STP to detect a change in the network and reconfigure the network can be quite long, leading to temporary network disruptions. Moreover, STP doesn't always make the best use of the network resources, as it only allows one active path between network nodes, leaving other potentially useful paths idle. These limitations led to the development of other types of protocols that improve on STP. These include Rapid Spanning Tree Protocol (RSTP), which provides faster convergence than STP, Multiple Spanning Tree Protocol (MSTP), which allows multiple active paths, and VLAN Spanning Tree (PVST), which provides a separate spanning tree for each VLAN, allowing more efficient use of network resources. STP is a powerful tool for preventing network loops, but it has some limitations which led to the development of other types of protocols. In our upcoming scenes, we'll dive into these other protocols and show you how they enhance the functionality of STP. Stay tuned. To overcome the limitations of STP, the Rapid Spanning Tree Protocol, or RSTP, was introduced. RSTP, as its name implies, is a faster version of the original Spanning Tree Protocol. It was designed to speed up the recalculation of the spanning tree when the network topology changes, which was a significant drawback of the original STP. RSTP accomplishes this rapid convergence by introducing new concepts and roles for switch ports. For instance, an alternate port in RSTP is a switch port that offers an alternative path to the root bridge, which is the central point of the network. If the current path to the root bridge fails, the alternate port can quickly take over, reducing the time it takes for the network to recover from the failure. Another key feature of RSTP is the backup port. This is a redundant port that provides a backup path to a segment of the network where another switch port already connects. If that switch port fails, the backup port immediately takes over the role of the failed port, ensuring a smooth transition with minimal disruption to network traffic. RSTP also introduces the concept of edge ports. These are switch ports that are never used to connect to another switch, only to end devices like computers or servers. By immediately transitioning these edge ports to the forwarding state, RSTP avoids unnecessary waiting times, thereby further speeding up the network's response to changes. Importantly, RSTP is also backward compatible with older switches that only support the original STP. This means that you can introduce RSTP in your existing network gradually, without having to replace all your older switches at once. In summary, RSTP offers several advantages over the original STP, including faster convergence times and backward compatibility with older equipment. It's a great improvement over STP and can help make your network more robust and responsive to changes. RSTP is a great improvement over STP, but sometimes a more flexible solution is needed, which brings us to MSTP. For networks with complex topologies, Multiple Spanning Tree Protocol, or MSTP, can provide the flexibility needed. Now let's dive into the world of MSTP, a powerful tool that can significantly enhance your network's performance. At its heart, MSTP is an extension of Rapid Spanning Tree Protocol, with the most remarkable difference being its ability to handle multiple spanning trees within a single network. This means that MSTP is capable of running multiple instances of the spanning tree algorithm, each corresponding to a group of VLANs. This can be a game changer for complex networks. By dividing a single large spanning tree into multiple smaller ones, MSTP allows for more efficient use of available network paths. This in turn can lead to better network performance, as traffic can be balanced across different paths, reducing congestion and improving overall network speed. So how does MSTP achieve this? Well, it's all about the concept of multiple spanning tree instances, or MSTIs. An MSTI is a logical grouping of VLANs that share the same spanning tree. Each MSTI can have its own root bridge and its own set of designated and blocking ports. This allows MSTP to optimize the forwarding paths for each group of VLANs based on their specific network traffic patterns. But what's really interesting about MSTP is its ability to interoperate with both STP and RSTP. Thanks to a special instance known as the Common and Internal Spanning Tree, or CIST, MSTP can communicate with other spanning tree protocols. The CIST acts as a sort of ambassador, representing all MSTIs in communications with STP or RSTP bridges. This ensures that, regardless of the protocols used in different parts of the network, all bridges can work together to prevent loops. And let's not forget about the role of the Multiple Spanning Tree Region, or MSTR, in MSTP. An MSTR is a group of interconnected MSTP bridges that appear as a single bridge to other spanning tree protocols. This allows for further optimization, as each MSTR can have its own set of MSTIs, each with its own root bridge and forwarding paths. In essence, MSTP is like a finely tuned orchestra, with each instrument, or in this case, each spanning tree, playing its part to create a harmonious network performance. It offers flexibility, scalability, and efficiency, making it an invaluable tool for managing complex network topologies. But as with any protocol, MSTP isn't without its challenges. Configuring and managing multiple spanning trees can be a complex task, requiring careful planning and a solid understanding of your network structure and traffic patterns. And while MSTP offers a lot of flexibility, it may not be the best choice for all networks, especially those with simpler topologies or less demanding performance requirements. MSTP offers a lot of flexibility, but sometimes a more granular control is needed, which is where PVST comes in. So stay tuned as we continue our journey through the fascinating world of spanning tree protocols. VLAN spanning tree, or PVST, allows for even more control over your network topology. When we talk about PVST, we're delving into a level of customization that's truly a game changer for network engineers. Imagine this: you're no longer confined to a one-size-fits-all solution. Instead, PVST provides the ability to have a separate spanning tree for each VLAN. You heard it right, each VLAN gets its own spanning tree. This means you can tailor your network's traffic flow based on the unique requirements of each VLAN. But what does this mean in practical terms? Well, think of it as having multiple lanes on a highway, each with its own traffic management system. With PVST, each VLAN or lane can have its own optimal path, independent of the others. This not only enhances efficiency, but also improves the overall performance of your network. Let's delve a bit deeper. PVST is actually an enhancement of the Spanning Tree Protocol, or STP. While STP provides a loop-free topology for a network, PVST takes it a step further by allowing different forwarding paths for different VLANs. This means each VLAN can take the most efficient route for its specific traffic, rather than following a single path set by the STP. It's like having your own personal GPS for each VLAN, guiding data packets along the most efficient route. This is particularly beneficial in large networks, where different VLANs might have different load requirements. But wait, there's more. PVST also allows for load balancing between VLANs. This means that traffic can be distributed evenly across the network, preventing any single VLAN from becoming a bottleneck. To wrap up, the beauty of pair VLAN spanning tree lies in its flexibility. It's like having multiple sub-networks within your main network, each with its own set of rules and pathways. This allows for a more efficient use of resources and a more reliable network performance. With PVST, you can optimize your network performance on a per VLAN basis, giving you the ultimate control over your network topology. We've covered a lot of ground today, so let's summarize the key points. We began our journey with an introduction to network loops. These are a common issue in network topologies, where data packets can endlessly circulate, causing traffic congestion and decreased network performance. To combat this, we delved into the Spanning Tree Protocol, or STP. STP is a Layer 2 network protocol designed to prevent loops by selectively disabling some of the network's paths, thereby ensuring a loop-free topology. It creates a tree that spans all the switches in an extended network, and it does this by using the Bridge Protocol Data Units, BPDUs. BPDUs share information on network topology between all switches in the network, helping to determine the best path for data transfer. Next, we introduced the Rapid Spanning Tree Protocol, RSTP. A more advanced version of STP, RSTP speeds up the network's recovery time after a topology change, making it more efficient. It achieves this by assigning roles to switches and their ports, allowing for faster reconfiguration and transition between states. Our journey then led us to the Multiple Spanning Tree Protocol, MSTP. This protocol is a significant upgrade from the previous versions, as it allows for multiple spanning trees within a network. MSTP offers the flexibility to group different VLANs into a single spanning tree, enhancing efficiency and reducing the load on network resources. Lastly, we explored the per VLAN spanning tree, PVST. This protocol creates an individual spanning tree for each VLAN, allowing for greater control and optimization of network resources. It enables load balancing, as traffic can be directed across different paths depending on the VLAN. Remember, each of these protocols plays a unique role in preventing network loops and optimizing network performance. STP forms the backbone, laying the groundwork for loop prevention. RSTP takes it a step further by speeding up recovery time. MSTP adds flexibility with multiple spanning trees, and PVST allows for individual optimization of each VLAN. Understanding these protocols is not just about memorizing their functions, it's about appreciating their roles in creating efficient, reliable, and robust network topologies. It's about being able to identify when to use each one and how to configure them properly to ensure optimal network performance. With a solid understanding of these protocols, you should now be able to confidently navigate and optimize your network topology.